Hello, my name is Sarah Neuwirth. I'm a postdoc at the Heidelberg University in Germany, and today I'm going to talk about parallel I/O optimization on Lustre, best practices, and the future. First of all, I would like to point out why scientific I/O is so difficult. Well, the main problem, or if you want to call it a problem, is that scientists think about their data in terms of science problems, which means when they write their algorithms, they do not think about the layout or the parallel I/O architecture underneath. They just simply think about molecules, atoms, crystals, particles, whatever can be applied to their science problem. However, in the end, their data will be stored in terms of bits and bytes of data on physical disks. In addition, the layers in between the applications and the physical disks add various levels of sophistication, which sometimes make it very difficult for scientists to apply best practices and I/O optimization techniques to their applications. First of all, we need to understand how large-scale applications or scientific applications write data onto the file system. In the single writer I/O pattern, one process aggregates data from all other processes and then performs I/O operations. This pattern is very simple to implement and easy to manage and can provide a good performance for very small I/O sizes. However, the pattern does not scale for large-scale application runs since it is limited by a single I/O process. It performs inefficiently for any large number of processors and data sizes, leading to a linear increase in time spent in writing. In the file per process I/O pattern, on the other hand, each process performs I/O operations to a separate file. Up to a certain point, this pattern can perform very fast, but is limited by each individual process which performs I/O. It is the simplest implementation of parallel I/O. However, parallel file per process I/O can quickly accumulate many files, and synchronizing metadata for a large collection of files introduces a potential bottleneck. Think about this, for example. Even a simple LS can break when being performed on a folder containing thousands of files. The next pattern I'd like to introduce is the single shared file I/O pattern. It allows many processes to share a common file handle but write to exclusive regions of a file. The data layout within the file is very important to prevent concurrent accesses to the same region. Contesting processes can introduce a significant overhead since the Lustre file system uses a log manager to serialize the access and guarantee file consistency. The collective buffering I/O pattern, on the other hand, improves the performance of shared file access by offloading some of the coordination work from the file system to the application. Subsets of processes are grouped in so-called aggregators, performing parallel I/O to shared files. This increases the number of shared files while improving the file system utilization. Also, it decreases the number of processes which access a shared file and therefore mitigates the file system contention. However, it can be algorithmically very complex to implement this pattern. The next thing we need to understand are some basics about the Lustre file system striping. So one of the main factors leading to high performance of Lustre file system deployments is the ability to stripe data across multiple storage targets in a round-robin fashion. Basically, files can be split up into multiple chunks that will then be stored on different storage targets across the Lustre system. On the figure on the right side, you can see an example where 3 files are being striped in a RAID 0 pattern across 3 available storage targets. So why is file striping beneficial to application performance? There are mainly 2 benefits. The first one is the file sizes. If you are able to place chunks of data on multiple storage targets, your file size is not limited by the space available on a single storage target anymore. In addition, the bandwidth can be significantly increased, your I/O bandwidth, because multiple processes can now simultaneously access the same file instead of being limited by a single storage device. If you talk about the file layout, aka the stripe pattern, the layout is typically selected by the Lustre client in either two ways. The first one is by policy. By policy could mean that you go with the default settings that Lustre comes with, or by inheriting the striping patterns from the parent directory. In addition, it is also possible by user policies, for example, the administrator user or the user application can set the striping pattern for a given file or a directory as well. Another important basic about the Lustre file systems is the file layouts supported by the Lustre file system. Originally, Lustre only supported the so-called plain file layout. The plain file layout is basically the example that was displayed on the previous slide, where you have a file, and the file is being divided into equally sized chunks and then distributed over a specified amount of object storage targets. Usually, the information is stored in a layout that is called, or in a structure that is called layout extended attributes, which are basically pointers towards where the data is actually located in memory. A recent feature that has been introduced by Lustre 2.10 is the progressive file layout. The progressive file layout relies on the composite layout internally, which is basically an array of sub-layout components, and each sub-layout is being described by a plain file layout covering different and non-overlapping extents. And in order to visualize what I'm just trying to explain you can have a look at this example being displayed down here. In this example, we have 4 non-overlapping extents, each with their individual striping pattern, their plain file layout. And the reason for introducing the progressive file layout is to simplify the use of Lustre so that users can expect a reasonable performance for a variety of file I/O patterns without the need to explicitly understand the I/O model or Lustre user details. And the idea is basically that the stripe layout changes as the file grows. The last Lustre file system striping internals that we need to understand before diving into the best practices is the actual standard stripe allocation methods. So the default allocator being used by Lustre when data is being placed on different object storage targets is the round-robin allocator. What happens here is that the round-robin allocator basically alternates stripes between storage targets on different object storage servers in order to evenly distribute the file among OSTs. The example that is being displayed here on the left provides a simple example with 8 storage targets and 1 storage server. And as you can see, we have 4 files, and each file has an individual stripe count, and the stripes are being placed in a round-robin fashion on the available storage targets, one after another. Or to provide a more generic approach to this algorithm, in this example, you can see basically highlighted by the colors 3 different storage servers, each with 3 storage targets. And you can see the arrows indicate how the round-robin allocator would alternate between the storage targets, then allocating the stripes on the actual storage devices. However, the round-robin allocator does not provide true load balancing, which is why there is another allocation method that is called the weighted allocator. And the weighted allocator uses a weighted random algorithm internally to fill emptier storage targets faster. However, because it uses a random algorithm, not always the storage target with the most free space is necessarily chosen, but one randomly from the ones that have a significantly less space used than other OSTs. So now let's have a look at user tools for striping. Now that we have understood that there are different file layouts and we can stripe, and we also know that there are different allocators, the user can actually set the striping pattern using 2 different tools. One is LFS set stripe, which is a very popular command line tool, and it allows you to specify or create a new plain file or directory with 1 single layout, or to create a new composite file or extend an existing layout with another extent. The example down here basically describes the striping pattern that was displayed in the progressive file layout example, where we had 4 extents with different stripe counts each. Another possibility to set the striping pattern is to use the Lustre API or user library called LL-API, which is provided by Lustre to set and configure the striping pattern for a new plain file out of a C program. However, this user library does not provide an API for creating or extending composite files. So now that we have learned about the Lustre file striping internals and that there are user tools that can be used to manipulate the striping pattern, we will highlight different best practices for file I/O. The first one I'd like to discuss is the alignment of data access. The stripe alignment of data can be critical. When using the file per process access pattern with a large number of files or processes, for example, it is best to set the stripe count to 1. So basically, to not use striping at all. Besides the stripe alignment, the size and location of I/O operations should be carefully managed. By mapping writing processes to a specific server, the number of concurrent operations on a single server can be reduced. This is especially helpful when file locks are handed out on a per server basis, which is the case for Lustre, to minimize the file locking contention. For single shared files, for example, you should try to minimize both the overhead associated with splitting an operation between storage targets and the contention between writing processes over a single storage target. The figure here displays 2 possible shared file layouts. The segmented file layout keeps the data from processes in a contiguous block. So as you can see, we have one single file and each writer has its own contiguous block where the data is being written to, while the strided file layout strides the data throughout the file, basically alternating chunks and writers in the same file, which could lead to an increased file locking contention, because what now happens is instead of mapping the whole block to a specific storage target, you might jump in between different storage targets and multiple writers will get in each other's way. Another recommendation that is broadly advertised by the Lustre community is to use high-level I/O libraries and MPI. Why should we use high-level I/O libraries? Well, there are a couple of main reasons for this. The first one is that it basically maps the application abstractions onto storage abstractions, which means that the scientist does not have to really understand the storage details underneath, and it also provides data portability. In addition, those high-level I/O libraries usually provide APIs which help to express scientific simulation data in a more natural way. So for example, you can write multidimensional data or non-contiguous data. Another important factor is that high-level I/O libraries usually sit on top of the MPI I/O layer and therefore can use MPI I/O optimizations. And then again, as mentioned before, they provide a portable format that can be basically copied between machines. And at the same time, it provides longevity. So basically the output will last and is accessible with library tools independently from the version number of the code. Another important recommendation that the Lustre community is advertising is to use MPI for communication. Even though you could use shared files to communicate data, it is recommended to use MPI for the actual communication. And because we can't dive into detail for every single recommendation that is out there, here's a brief summary of recommendations out there. So the first 2 ones I have been discussing with the stripe alignment and the reduction of the file locking contention by carefully managing the data placement. Another important thing is that you should do large I/O, which basically means it is better to write have fewer write requests with big chunks of data. So meaning full stripe width or greater, rather than a lot of small bursty I/O. And then again, use high-level I/O libraries and MPI for communication. And obviously, you should perform parallel I/O, not single writer I/O. Otherwise, your program won't be able to take advantage of the system's parallel capabilities, and the bandwidth will decrease and will be bound by your one writing process. And then last but not least, another important recommendation is the user should have a good understanding of how and how much the application outputs before tuning the striping pattern. Otherwise, tuning the striping pattern might result in a decreased performance. So, taking all best practices into account, the following striping recommendations can be summarized. On the left side, we do have the plain file layout. So the first two ones address basically the file per process pattern. So if your number of files exceeds or equals the number of storage targets available in your system, you should have your main goal should be the reduction or to reduce the Lustre contention and the storage target file locking. And this can be achieved by setting the stripe count to 1. If your number of files is less than the number of available storage targets, you should try to utilize as many storage targets as possible to maximize your access performance. And this is done by setting the stripe count to the number of OSTs divided by the number of files. If you're using the single shared file pattern, what you should do is to try and maximize the parallel access performance. And this is being done by setting the stripe count either to the number of aggregators if the number of aggregators does not exceed the number of OSTs, or to the number of OSTs otherwise. For progressive file layouts, it's a bit more difficult to make such specific recommendations as there has not been much research done in that particular area. But there are two main recommendations that can be followed. One is that your file layout should not exceed or should stop growing at the point where the total number of stripes equals or exceeds the number of storage targets you have available in your system. And closely tied with this is to avoid oversubscribing storage target bandwidth. Basically, your layout or your progressive file should not reuse storage targets that have been used at the beginning of the file. So what I did next is I used all of the best practices and applied them to two application runs, one with the IOR benchmark, which can be used to evaluate read and write performance, and one with the HackIO application kernel, and I did it for two different setups, IOR with each with 16 processes, but generating less or more data, same for HackIO, but with particles instead. And I compared the plain file setup in the file per process mode with the progressive file layout setup with the file per process mode with 4 extents. And the results show that with the default Lustre deployment that uses the round robin allocator to place stripes on storage targets for each job, there can be a significant load imbalance at the server level. And the load imbalance persists at different scales and different striping layouts, and thus can lead to imbalanced resource usage and resource contention, and also heavily impact your read performance. Later, if you, for example, need to reread your checkpointing data or need to reread your data for visualization or post-processing purposes. So taking this into account, I would like to point out some recent research efforts that have been done in the domain of improving I/O for Lustre. And there are two different approaches. One is the client-side approach, and the other one is the server-side approach. So I've been mainly focusing on the client-side approach, and the beauty about this is that you can apply it per job, you can provide a transparent implementation, however you lack the global view. On the other side, you have the server-side approach, which provides a global view of storage servers and is able to simultaneously allocate resources, but does not know anything about the file layouts being used, and most of the times requires code modification. So this work has been done by researchers at Virginia Tech, and so we thought, why not combining them? Because both of them have equally good merits. So if we combine them, we can rule out the disadvantages and come up with a great tool, and that's what we did. We created EOS, an end-to-end control plane architecture, and it consists of client and server-side components. And basically what happens here is on the client side, when you initially run applications, there's a tracing tool running in the background, which captures your I/O characteristics and feeds them through a parser into a prediction model, which is based on the autoregressive integrated moving average model, or short ARIMA. And the information out of this tracing path is being forwarded into the configuration manager, which basically uses the prediction of future requests and the configuration. For example, if you want to use PFL, you could provide your own extent definitions, or you can go with the default ones, and feeds that back into an interaction database that can be accessed by the metadata server. On the server side, on the other hand, you collect real-time statistics of all of the storage servers and of the metadata server. And all of those statistics are being collected and fed into the OST allocation algorithm in order to ensure that these resources are equally utilized. And then the OST allocation algorithm feeds the set of OSTs to be used back into the interaction database. The interaction database, on the other hand, can be accessed by the placement library, which is a transparent library that can be preloaded by a user application and transparently intercepts application I/O calls by using LLAPI. It creates the metadata for I/O requests and places those on the metadata server, and eventually the data will be written load balanced onto the storage targets. I would like to conclude my talk by providing an overview of the performance evaluation. What we did is we compared the best practices basically applied together with the default allocation methods in comparison to our ES tool. And we did it for 2 different PFL configurations and for different file layouts and sharing patterns. And the outcome of our performance evaluation shows, so for excuse me. So for the utilization, here in the case of file per process, but we achieved equally good results for single shared file, is that, for example, in the case of OST utilization with IOR, non-PFL, so plain file mode, what you can see here is that the comparison of load under ES and the default round-robin allocator, and we see the storage target utilization for the IOR benchmark with varying data sizes. What can be observed is that ES balances the load on all storage targets in a near optimal manner. So for example, for 16 processes and 32 GB of data produced, the round-robin approach, there can be a maximum load observed for the round-robin approach on object storage targets 19 and 18, where the utilization is up to 25%. While in contrast to this, the maximum load observed under ES is 18%, which is near optimal. Optimal would have been 16.6. And the same can be observed with the progressive file layout, even with a better results when it comes to load balancing. And what we also did is we compared the object server utilization, where we achieved optimal results. And we also wanted to verify that this approach works in a diverse I/O environment, basically having multiple applications being run at the same time, potentially from different clients. And that's what we did in the right corner. And what we did here is we ran IOR and HackIO, 2 very different I/O patterns simultaneously. And we even mixed 2 different PFL configurations. And as you can see, ES still performs in an almost near optimal manner. As for write and read performance, for read performance, our ES framework excels, and we achieve up to 43% of read performance improvements compared to the round-robin allocator. And this is achieved by load balancing everything evenly across storage targets and object storage servers. For write performance, we still observe that we're either on par or slightly worse than the round-robin write performance, which is probably due to the negligible overhead, and we're still performance tuning. So overall, we're pretty happy about the outcome and think that ES is a valuable tool to improve the overall performance. In conclusion, the inconvenient truth is that users need to have a good understanding about their application code. They need to be familiar with the recommended best practices, and they need to know how to apply them. And at the same time, every time code is ported between machines or between upgraded file systems, users are required to make changes to maintain their performance. So I would argue that the current status of Lustre has potential for further improvement. We have shown that the standard stripe allocators do not provide true load balancing, and Lustre could benefit from global statistics and a feedback system. Thank you for your attention. Questions?